Let's recall Frostman's lemma. We used it to give lower bounds on the Hausdorff dimension of product A cross B of subsets of Euclidean spaces. In this video, we want to talk about another application of Frostman's lemma. In fact, this one is the first time people usually see Frostman's lemma. But anyway, here is a recall of what it says. If you have a subset, a Borel subset, indeed, Frostman himself, around 1935, proved it only for closed sets, and later this was generalized to all Borel sets. Anyway, if you have a Borel subset with positive S-dimensional Hausdorff measure, that is equivalent to the existence of a very special measure, sometimes called Frostman measure, with the properties. The key property is this inequality down here, but of course other properties must also connect it to the subset X. So number one, the support of that measure is restricted to X, so that measure really concerns the set X, and it has finite and positive measure for the whole space. By multiplying with a constant, you can assume that the measure of the whole space is equal to 1. In another word, it is a probability measure. So after these preliminary assumptions on mu, which basically just say that it's a reasonable measure having something to do with the set X, the main condition which establishes the if and only if claim is that the measure of balls are bounded from above by s power of the radius of the ball. Of course, there is no point in putting a constant here. By multiplying with a constant, you can always assume that this is the case. So this is for all points in Rn and all radii. So this is both ways. In other direction, if you succeed in finding such a measure, then you immediately see that this is positive, from which also you can conclude, and that will be the application for today, that the dimension of the set X is at least S. Okay, so what is the application of Frostman's lemma, this theorem that I meant for today? That application has to do with finding, so the application is proving the lower bound HS of C positive for counter type, not just counter necessarily, sets, which then, so once you establish this, proves that the dimension of the counter set is what we suspect. So where does this come from? Remember that by its very construction, when you construct a counter set, you have a covering of the set with countable union of sets. In this case, they will be the approximating finite step constructions of the counter set. So the union of these line segments, if you are in R1, is a covering of the set, and usually that establishes the upper bound that HS of the counter set, which is the union of all these steps, is finite. So you usually establish this very easily just by definition, using the very sets that are used in the construction to give this upper bound, from which it follows that the dimension of the counter set is at most S. And S is something that we guess, maybe by just counting or a little bit of cheating using other notions of dimension. Now, we don't know if dimension is equal to S, because it could be that HS of C is 0 and H is minus some number a little bit smaller of C is finite, in which case the dimension will go even further down, more than S. So to establish that the dimension of the counter set is actually equal to S, we need to establish that also Hausdorff measure is bounded from below. It's not 0. And this is where we can use the equivalence given by the theorem to, instead of proving this, we try to show, rather than construct really, that such a measure exists. And why is it even possible or easier, based on what I'm telling you, that to come up with such a measure? This is so abstract, and this theorem doesn't give you a way of finding it. In the special case that we are dealing with here, with the kind of self-similar sets, the idea is that at each step you assign a measure. So here you assign the probability measure mu1. So you just equally divide 1 between them. So you assign 1/2 to this set and 1/2 to this set, and that's your measure. And within each segment is just a scaling of the Lebesgue measure. So for this level then, you have measure 2, which is again quantity 1 equally distributed between these line segments, and you keep going. And from general theorems about measures, it turns out that there exists some, again, probability measure such that maybe after passing to some subsequence, these measures converge weakly, and this weak convergence is enough for us, to that measure mu. Now, each one of these satisfies this upper bound of radius to power s, and it carries on to this limit measure that this also has that upper bound. So therefore, this mu becomes a Frostman measure on the limit set C, and that is there. So that gives us the existence of a Frostman measure, and from which, according to the theorem, it follows that the HS of C is positive, and that dimension of C is at least S, which together with this upper bound ends the proof that the dimension is equal to S. This cannot, of course, be used for computing the actual measure of the set C, only for confirming the dimension. So that is usually the first time people see Frostman measure. This is very closely related also to the mass distribution principle. What I was doing here in constructing mu case was just to distribute the mass of 1 among the pieces. But the real reason I didn't go into too much detail is because Azam has covered this beautifully in his videos, and I will put a link at the end of this video to his, where probably he gives more details. Also, he has other videos where he talks about the notion of weak convergence of measures in more detail again. So I want to overdo it, as his videos are also clear and beautifully explained. So this is our second application of Frostman's lemma. I'm looking for more of applications of Frostman's lemma, and if I find them, I will share them with you. All in all, this is a beautiful theorem with connections to many other topics in geometric measure theory. Thanks for watching the video, and please consider subscribing, as we are reaching the 400 pretty soon. Have a good day.